Hi, everyone. Welcome to Cincinnati Software Craftsmanship. I am so happy to see you all today. Apologize. Give me 1 second. I am having a small slide difficulty. We'll get it all straightened out. We're going to be running without slides for the very first part of this talk. So that's not a big issue, but we'll work through it. All right. So thank you for joining us on this fine Wednesday. I'm going to drop a little wave in the chat here, of course, just to say hi. One of the things we like to do, feel free to wave back and say hi yourself. Tell us maybe where you're from. That would be fun. As we do every month, I'll ask you to follow us on our social media platforms. So Facebook and Twitter and YouTube and then also we stream our videos to Twitch and YouTube. We're also streaming to LinkedIn for the first time, so we'll see how that goes. Let us know what you think of that, if that's useful to you. Also want to say thank you to Kroger Technology for sponsoring the meetup. And of course, to the software craftsmanship organizers. Now, I want you to, as a reminder, to stick around after the talk. We'll be giving away a license for anyone JetBrains product, and we'll also be giving away a copy of Felienne's Feliene's book. Like last month, we're going to start the giveaway registration right now. This will give you plenty of time to sign into Twitch and register for the giveaway. As a small bonus to our Twitch followers, you get a better chance of winning. So you know what to do. To enter, all you have to do is type #CSC in the chat. The MooBot will jump in there in just a second and give you those instructions as well. With that, we're going to give a virtual, where normally we give a big welcome to, I'd introduce the speaker and then they'd pop on here. But since tonight, we're doing something a little different. We're going to be doing a virtual talk. So we're going to give a virtual welcome to Felienne, and then we'll play the recorded talk. And I think you all will enjoy it very much. So let's learn about reading complex code.
Hello, good evening, everyone. Welcome to this Manning Books live stream on Twitch today. My name is Felienne Hermans, and today I will explain to you how to read code, specifically how to read very confusing code and what confusing code creates in your brain, what type of tension is created in your brain if you read confusing code. If you have any questions, feel free, of course, to drop them in the chat. I'll be keeping an eye on the chat on my second screen. So if you see me do this, then that is because I'm looking at your questions. So feel free, of course, to reach out if there's anything more you want to know. Before we dive into the topic of confusing code, I actually want to take you back into my own personal history to explain to you why I started to research complicated code, why I started to research code reading and code comprehension, the process of understanding code by people. This isn't because I started that. I was a researcher already when I started working on this, but I was actually working on other things. I wasn't working on code comprehension. But then in the year 2013, what happened is I started to teach kids at a community center. So I was already teaching at the university, slightly older children, adults of student age. But in addition to that, on Saturdays, I started to teach in a programming club for kids. And these kids were like 8, 9, 10-year-olds, so pretty young kids. And they asked me if I could teach them programming. So then I was like, yes, sure, children, no problem. I can teach you programming, even though I didn't really know that much about teaching. I of course knew how to lecture. I knew how to, at the university, to talk to a bunch of students, but that was really different from teaching kids. But I didn't let that stop me. I thought, I mean, they're kids. They're 8 or 9-year-olds. How hard can it be, right, to teach them programming? And then what happened is that subconsciously, I started to think about how I learned programming when I was a kid. So this is me. I'm about 10 years old here, sitting behind my dad's computer, programming away. That is how I learned programming at a relatively young age. But I didn't have a teacher. There was no one teaching me programming. I mainly learned programming from books. I had this book, Basic Computer Games, and maybe if you're the same age as I am, you might also have learned programming from this type of books. And in these books, there wasn't something like an explanation. It wasn't even very much a tutorial or a book that explained you something. If you opened the book, this was what was inside. Just printed out basic listings that you could manually copy into your computer. And then, of course, you made many mistakes, but you fixed all the mistakes. And then after a while, you had a program. That's how I learned programming. So again, there wasn't someone teaching me programming. I more or less taught myself. And that's not just me. Many people my age, children of the 80s, so to say, all have learned, or many have learned programming in this way, because when we were kids, there weren't so many adults that knew how to program, and there was no YouTube, so there weren't tutorials either. So the best way at that time was just to try stuff out until it worked. Just let kids explore, let them figure out how to do it by themselves. That vibe of self-exploration is still very much present also if you look at programming books today. So my strategy in the programming club was, let's buy a bunch of books for kids, just like I learned programming from books, and I'll bring the books to the computer club and the kids can learn from the books. In those books, you can clearly see that they are written by people that share my experience, that grew up teaching themselves programming to a certain extent. I have a few images from books here. The images will be in Dutch, but there's always an English translation underneath if you're not so fluent in Dutch, which I could understand. So what do coding for kids books say? For example, the best part of programming is finding mistakes. Which is like a weird thing to say, right? The best part of programming is finding mistakes? I don't think so. I love programming, but the best part is finding mistakes. I mean, half of the time, I'm the person that puts in the mistakes. I don't really like finding mistakes. Maybe fixing mistakes, but finding mistakes? It's not really my favorite. Programmers only learn from making mistakes. That's also very much this perspective of, I figured it out, I tried a bit, and then, there was a mistake, and then I tried a bit more. But of course, there are other things that can result from mistakes, apart from learning. Some kids, if they make many mistakes, maybe they're just like, table flip. I don't care anymore. And there are so many mistakes. I don't see a way out. I don't think I actually like this as a hobby. So this is clear survivorship bias. People that made many mistakes and learned from them, they are now programmers writing these books. Whereas people that made many mistakes and they thought, wow, this is super hard, they didn't grow up to become programmers that later became programming for kids authors. You will fail often and it will be frustrating. Beware, children. This is also special, right? Of course, it is true. Of course, if you learn programming, if you learn anything, you will fail often and it will.
Of course, I clicked the wrong button and dropped the stream. So give me 1 second to get that started back up.
evening, everyone. Here's a bunch of books. I turn on the computers. If you make a mistake, the computer will tell you. Basically, the teaching philosophy that I had there, and that 85% will to a certain extent be self-taught learners. Should I break? This also our profession is difficult and that it isn't grow up to become programmers that later became programming for kids authors. You will fail often and it will be frustrating. Beware, children. This is also special, right? Of course, it is true. Of course, if you learn programming, if you learn anything, you will fail often and it will be frustrating. But why do we tell kids this, right? Compare this to a book about learning to play soccer, for example. This will have nice pictures of famous soccer players, and probably it will say something like, well, soccer, maybe it's hard, but if you practice a lot, you too can be a professional soccer player. Certainly it will not say soccer is hard and it will be frustrating. It will actually encourage trying, but it will not stress the difficulty. This is a very programming specific thing to say, where as a community, we sort of like that it's hard, right? We like that our profession is difficult and that it isn't for everyone, maybe. Here's another one. Never be afraid to mess around and experiment. Break the rules. So I think, breaking the rules is pretty good, solid life advice. I like to break the rules now and then, but breaking the rules in programming, does that make sense as an advice? This book, Computer Coding for Kids, is about a programming language called Python, that I guess many of people that are viewing today are familiar with. So Python, like most programming languages, has a bunch of rules that you cannot break. This is a page in the same book. So this says a colon goes there, a quotation mark goes there, a rectangular bracket goes there. Not a round bracket, not a curly bracket. No, it has to be a rectangular bracket. Those are rules you cannot break. So this advice about rule breaking is very much the perspective of someone that has already ascended to expert level. Someone that has already broken what we call the syntax barrier. Someone that can see through syntax and that is no longer bothered by small mistakes. But of course, if you're a beginner, what is the difference between a round bracket and a rectangular bracket? And why is that a rule I cannot break? What rules should I break? This also is advice that very much fits the survivor bias of someone who is now an expert projecting on children. And most importantly, it's fun. Most importantly. So notice what this doesn't say, right? It doesn't say programming is a really good career and it can easily make you a solid living. Or programming is a means of expression. It's a very creative thing to do and you can build whatever you want. No, none of that. The most important thing is that it's fun, which again is a perspective of someone who has enjoyed learning. And especially the combination with this is hard and this is frustrating, but also you have to like it. And also there are magic rules you cannot break, but break a few other rules. It's all not very helpful as advice. As a community, we are projecting sort of weird things on kids that want to learn programming. And as I said, this is a perspective not just shared by me. What you see here are the results of a survey on the website Stack Overflow that I guess most people listening today are familiar with. This survey was done among 90,000 programmers, so a pretty solid sample of programmers in the workforce today. What you can see here is that 85% of programmers in the workforce today learned programming before the age of 19. So before they were in university, before they were adults. And a big part of that 85% will to a certain extent be self-taught learners, because many countries don't really have programming at the high school or middle school level. So a big chunk of people in the workforce today also learned programming alone by themselves to a certain extent, being self-taught. And this leads to a culture in which people that teach programming very often let kids explore. That's very much how I started to teach when I started to teach programming to kids. Just let them explore. Here's a bunch of books. I turn on the computers. If you make a mistake, the computer will tell you. Basically, the teaching philosophy that I had there and that many people have is the compiler is the teacher. If you make a mistake, you get an error message. It tells you what to do. A teacher might not be all that necessary. Of course, we don't say that like literally aloud, but that's the culture that underlies many of those programming lessons. Certainly, it did underlie my programming lesson. Unsurprisingly, especially to people that actually know about teaching, kids were like, wow, that is really hard. We tried something, but we still don't know how to do it. Kids would ask me the same question every week. They'd be like, okay, I want to have an extra level in my game. How do I do this? And I would be like, well, this. Try it. And then the next week, the same kid would be like, okay, but how do I add an extra level? And I was like, well, I explained this to you last week. How do you not remember? And I really didn't understand why they couldn't remember. I didn't understand that saying something, like the fact that this knowledge has exited my mouth, didn't mean that it even entered their ears, let alone entered their memories. So at this point, I also became like sad and frustrated. And at that point also my scientific curiosity kicked in. Because as I said, I was a scientific researcher at that point. I just wasn't researching programming for kids. I was actually researching professional programmers at that point. But then I thought someone must have looked into this. And indeed, they had. I found this paper called Skill Progression Demonstrated by Users in Scratch, where Scratch is a programming language specifically made for kids. And this paper found that many kids start to program and then stop programming. So there's a really high dropout. And this was a study that only looked at data. So there were no interviews. So we don't really know why the kids dropped out, but maybe it had something to do with programming being really hard and frustrating, and you should enjoy that, otherwise you're just not made for it. What this paper also found is that children, after a while, flatten their skill level. So initially kids learn quite a bit, but then after a while, their skill level drops. They don't acquire new knowledge anymore. And that also really fitted with what I saw in the programming club, that initially, of course, they learned a bit and then they didn't advance, and I didn't understand why. Fast forward a little bit to 2020. Last year, a paper came out that is called "If They Build It, Will They Understand It?" And this paper basically says, well, the answer is no. If kids build something in a programming language, that doesn't mean that they understand it. So these people actually did a study in which kids were observed, not just their data was analyzed. And they looked at if a child makes a program with, for example, a variable in it. If you later quiz them, give them a test on variables, the fact that it occurs in their program, does that mean that they can correctly answer quiz questions on a topic like loops or variables? And the answer was no. So very often kids can use a variable in a program, but they don't really understand it. Probably they came to the solution by looking what their next door neighbor was doing, or looking on YouTube, or just trying out many times. So just the fact that a kid can do something doesn't mean that they really grasp concepts, which also fitted with what I saw at the programming club, that kids were doing stuff. Like they were making games and they were sort of happy, but they would ask the same question every week. They weren't learning, even though they were sometimes having fun and they were making programs. So back to 2013, I didn't know most of that at the time. I just knew that the kids were learning and I didn't know why. And again, I didn't really know that much about learning. And you might think, well, wait a minute, didn't you just say you're a professor, that you were teaching in a university? Well, yes, but in the Netherlands and also in many other countries around the world, we have this fantastic system where if you want to teach elementary school, you go to school for 4 years. If you want to teach in high school, you go to school for 5 years. But if you want to teach at a university, you just get a PhD in any topic like astrophysics or software engineering, like I did, and then 12 afternoons of educational training, and then you are good to go to teach. So technically, I was teaching qualified, but that didn't really mean that I had a working understanding of how to teach, specifically on how to do anything else than just say stuff and hope that it magically stuck to children's or students' brains. But at that point, I started to get really, really interested in learning, specifically because the kids in the programming club were struggling so much. Now, clearly, my undergrads at that time were also struggling because I just wasn't doing such a great job in teaching. But the nice thing about an 8-year-old that is confused is they will tell you. Like, one of the kids in my club at one day came to me after class and he looked me in the eye and he said, I am not coming back to this stupid programming club. And I was like, oh, right in the feels. What are you saying? But he was right. I mean, he wasn't learning anything. But that really hurt, not just because it hurt, but also because I thought to myself, if I can get an 8-year-old that voluntarily comes to a community center on Saturday to learn programming, this is on me. Like, it's not because he's not motivated, he isn't willing to put in the work, he's showing up and I am failing him. So then I was like, man, I have to get better at this. So that brought me to start to research how people learn. How do people learn anything? Like, I had no clue. So I started to really deep dive into how people learn things, and specifically how people acquire languages, how people acquire their first natural language. So one of the things I read, which I can really recommend if you want to read about how people learn to read, is the Oxford Handbook of Reading, which it does stretch the definition of a handbook a bit. It is like 600 pages, but it has so much information about how kids learn their first natural language. And the first thing I learned from this book is we never teach reading code. We never teach how to read code. This just isn't a thing that comes up. Not in universities, not in programming clubs for kids, not in boot camps for adults that want to go into coding. It's just not a thing we explain. Like, I had kids in class that were like, hey teacher, I made this program in Scratch last week, but I don't really remember like how it works. Can you help me? What does this do? And then I would be like, well, child, what do you think it does? And this was very much this culture of never be afraid to mess around and experiment. I almost literally said to the kid, well, kid, don't be afraid to mess around and experiment. Just try it out. But I didn't in any way help them to read the program. And if you compare that to reading natural language, if your kid goes to school, we don't say, hey, children in grade 1, here's the alphabet. Now here's a book. No, they practice all the time. It's like, cat, book. We teach them strategies as well. We teach them strategies for how to read words. In the Netherlands, when we teach this, usually we use this motion. So kids are taught with every letter to use this motion and then to glue the letters together. We teach them tricks that help them read. But then for this program, how would you even read this? So this is Scratch, a visual language, and all these scripts are ran in parallel. And it's event-based, so maybe if you can read, depending on your screen, if you can read what the code says, they're events. So when up arrow is pressed, when I receive a certain message, when down arrow is pressed, and when I receive another message. So all these scripts are sort of running at the same time in something like a game loop. And when an event happens, they are turned on, so to say. So how would you read this code? It's not even like imperative Python code that you could read top to bottom. It's not even an easy question to answer for me as a professional, how you would read this. And we never gave kids any strategies on how to read this. And then, of course, the kid was like, I don't know. It's like, what do you think? The kid is, I don't know. You never explained anything to me about how to do this. Clearly, I don't know. And again, compare this to reading your first natural language. Imagine you have a 5, 6, 7-year-old at home, and you're like, Mommy, what's that word? You probably don't say, well, honey, what do you think it says? That's not helpful. You probably help them break down the problem. Like maybe you point at the first letter. You're like, that first letter, do you recognize it? It's the first letter of your little brother's name. You know, he's called Albert. It's also, do you recognize the letter? And then the kid is like, oh yeah, maybe that's an A. So you ask them to know the first letter. Or maybe you look at clues in the vicinity. Where does it say apple? Maybe you're in the supermarket and it's next to the apples. So you can also teach them, hey, maybe you want to look at the context. What could this mean based on what you see? But you would help them figure it out. You wouldn't just say, oh, what's that? But then the kid might say, cat, dinosaur, I have no clue. And this isn't just teaching in school. So you might think, well, now you're comparing programming, very often done outside of school, with things we teach in schools, like reading. But it isn't just reading. It's also music, for example. If your kid wants to play a musical instrument, the teacher also doesn't say, well, here's a guitar. Just try whatever works for you. Oh, do you want to learn tennis? Well, here's a tennis racket and 2 balls. Just make up some rules. For all of those things, we break up the problem in small steps and we practice the small steps. In tennis, you might want to practice the backhand and the forehand and the service. And in guitar playing, you might want to play the note C 100 times until you get your fingers correctly. And only then you move on. So from all these perspectives, both inside of schools and outside of schools, practicing small skills is the key to getting better. And then we never practiced the skill of reading code. That was weird. When I started to dive into reading, I didn't understand why we don't teach that explicitly. And this really isn't exclusively an issue to children. I'm still also teaching undergrads, and I have had 2nd or 3rd year students that needed to read a piece of Python that they handed in, or that one of their teammates handed in. It's like, okay, what does this code do? Where is the error? They would literally start at the top of the file and just read all the lines. And then at first I'd be like, that is not very smart. Why would you do that? Why wouldn't you just follow the call stack? But then I realized I had never taught them to follow the call stack. I don't remember how I picked up that was a good strategy, but no one told me to do that. So clearly there's a bunch of people that can learn it on their own, but there's so many more people that could also learn it if we would just tell them. So we don't teach reading code, and that's really something that now I'm working on. Of course, now that I'm teaching children and undergrads in the proper way, certainly now I'm teaching them how to read code. That's actually what we will be talking about a little bit later on in this stream as well. What I also found from studying what people do in other fields is that not just we don't teach reading as teachers, but also as professionals, we never practice reading. If you want to be a good guitar player, you don't stop to practice small things after you had guitar lessons. You will continuously always hone your skills. You will still do C, D, E, F, G before every show, even if you're a professional. So we don't really practice reading. Whereas research shows that code reading is very important for our practice. This paper by Xia et al. Shows that professional programmers spend 58% of their time reading code. So almost 60% of the time, you, professional programmer in the audience, are reading code. Yet, when do you practice to read code? Never. We always think that if you want to get better at programming, you should do more programming. Advancing in programming is writing more programs. And we really like to celebrate Saturday night open source projects. Oh, you need to have a hobby project to be a good programmer. Some people go as far as to say that if you don't have a hobby project, you're not a proper programmer. We always think that if you want to get better at programming, you should program more. Never be afraid to mess around and experiment, right? Try out stuff. That's important. Maybe recently, 2 months back, it was December, people were participating in Advent of Code, which is fun. Like, I love Advent of Code, but it does show that we do see getting better as writing more. It wasn't an Advent of reading code. It wasn't like, oh, every day of December, we will give you a code snippet and you just have to figure out what it says. No, it is here's a prompt and you write code, which is much of how I spent my undergrad days was here's a problem, like reverse a linked list and write code, and how I taught as well, and I think how many people were taught, very much with a focus on writing code as a means to get better at programming. So we don't really practice code reading either. And then the third thing that I learned from looking at how other fields have their stuff together is that we don't really have theories for reading code. Like, what happens in your brain if you read code? I don't know. But I also, at this point, didn't know that other people do know. But fields like natural language actually have a pretty solid understanding of how your brain processes text, processes words. I was like, wow, that's so cool. I didn't know you could even know that. So that's what I want to talk about in like the rest of the half hour we have today is what happens in your brain when you read code? And what do we already know from what happens in your brain when you read text that we can use? We don't have to reinvent the wheel. People know this, and we can just use what natural language already knows. So what do we know about code reading or about reading language? When information enters your brain, it first enters the short-term memory that I guess you have heard of. So firstly, information is stored in your short-term memory for a brief period of time. You can think a bit of this as your brain's RAM. Information can be stored there briefly, and it's a lot smaller than long-term storage. And this has been known for a pretty long time already. So George Miller in the 1950s already said that your short-term memory is really small. It can only hold between 5 and 9 elements. So it's really, really tiny. Let's actually try that in practice. So I hope you are participating, looking at the chat as well in the meantime. I hope you are participating. I will show you a brief sentence, just a sentence of 3 words. And it is your job at home to remember and reproduce the sentence. But I will show it to you for a very brief time. It's like half a second. It will be like, and it's gone. Just to show you how small your short-term memory is. So I hope you're watching at home. There we go. Prepare. So I guess you're screaming at your phone. I'm like, this is unreasonably hard, Hermans. This is undoable. We cannot do it. Well, I'm sorry. That's just how small your short-term memory is. It can only hold between 5 and 9 elements. Actually, newer research even suggests it might be smaller. It might be between 2 and 6 elements. In any case, it is really, really small. So now you might wonder, well, if our short-term memory is so small, how do we do anything? Like, how is it possible that I can speak in a language that isn't even my first language, and also wave my hands and also occasionally look at the chat messages. How is that even possible with such a tiny brain? Well, your short-term memory doesn't work alone. It actually collaborates in your brain with your working memory. So if you have read a sentence, then from the short-term memory, it is sent on, processed through the working memory. But in the working memory, not just information from your short-term memory is stored, but also information from your long-term memory. Your long-term memory really helps your working memory process. And of that we will also see a small example. So I'll show you yet another sentence, and there you can see that your short-term memory can be supported by your long-term memory. Here we go. I hope you're ready for yet another sentence. So that felt doable, I guess, right? It was still hard. I know it was still quite hard, but at least now you could make sense of what was there. Probably you could understand a few letters. Not because it was substantially, like inherently easier, but those letters are things you've practiced. So often you've looked at letters that you can very quickly recognize and remember them. And I will show you even how your long-term memory can support your short-term memory so that you can remember a sentence, something that seemed undoable just a few minutes ago, suddenly turns out to be relatively easy if your long-term memory helps you. So I'll show you a third sentence, and I am sure everyone can do it. If you just don't blink and don't miss the sentence, you can remember this 100%. Here we go. So that was easy, right? Even though it was the exact same length of the first sentence and the second sentence. But what happens here is you can quickly understand this. Remember this. Why? Because you're not remembering half a circle and a circle with a comma attached to it and a Catholic cross and a long stripe and a tiny circle. You're not remembering like that. You can immediately recognize the letters because you've seen them so often. And then not only are you recognizing the letters, you are recognizing words. You are saying, not in your memory, C-A-T-L-O-V-E. No, it's like cat, it's one thing. So those things are retrieved from your long-term memory. You know the letters, you know what a cake is and what loaves is. So the number of things you have to remember now has suddenly decreased from all the individual letters, which are way too many, to 3 things, which easily fit your short-term memory. So here you see in action the collaboration between long and short-term memory. So now let's circle back to programming, because it sort of turned into an introductory cognitive science lecture, which is also interesting, I guess. But I know most of you came here to listen, to know about getting better at reading code. What happens in your brain when you read code? So let's look at 3 different programs, because with the different forms of memory, short-term memory, long-term memory, and working memory, come different processes related to code, different reasons why code can be confusing. So let's look at this program. It's a program in a programming language called APL, which is sort of a weird and esoteric programming language that most professional programmers don't know. It's very old. It's from 1960, and it's mainly meant to do vector calculations. So I'm just going to assume that this program to you is confusing, because the program is 22222TN. This is the program. This is an entire program in APL. So why are you confused by this? It's because of the T. You don't know what the T does. You probably know what 2222. You know that it's twos. And I will tell you that the n is the input parameter to this program. So you know what that is. It will be a number as well. But then what is that t thing? So this is an issue with your long-term memory, right? You just don't know what the t is. It's not because you're not capable of processing this program. You just don't know what the thing is. No one ever told you what it is. So you have a long-term memory issue. This program, a Java program, also might be confusing to you, especially if you're not a trained Java programmer. If you're, like me, mainly using Python as a programming language, then this might be confusing because it overloads your short-term memory. If you really want to understand it, you have to remember many things. Public class, binary calculator, public static void, main, int, end, system out, print line, integer, binary string. If you're an experienced Java programmer, you probably know that public class and public static void main is all not so important. Probably where the importance are is in the binary string and the binary calculation. But you can only see that if you're not all too confused by all the fluff that is there. So this program is a bit fluffy, and if you're not used to it, this will be heavy on your short-term memory. Here is a third program. By the way, they all do the same. All these programs calculate the binary representation of the number n. Here's a program that's also confusing, probably, but it's confusing for yet another reason. Here, the program is confusing because you have to do so many things. It is your working memory in this program that is being stressed, is being stretched to its limits. Because what is going on here? You can't really see. Probably if you would actually have to debug this program, you would take a pen, you'd say, okay, well, let's just try this for the value n. Okay, so n is 7. What happens? Okay, so b is the empty string, and then this loop goes from 7 to 0. Okay, so then n is, okay, that's 7 divided by 2, so that's 3 because it's rounded. Okay, so then b string is, okay, so it's a string 0. Okay, what happens in the next iteration? So you just have to work really hard to understand this. If you're somewhat familiar with programming languages, even if you're not familiar with BASIC, you will know what most of this does. You know let, you know the equal sign, assignment, you know the empty string, you know a for loop. Your long-term memory is fine, right? The issue here is your working memory. You have to do so many things. So you might be like, yes, but what you've just showed us just means that reading code is really hard. Look, you showed us all these types of confusion. And that might lead to what I sometimes think is so sad, that people, they look at a certain library, like I sometimes do this, oh, I need a parser library in Python, let me go on GitHub. And then you look at code that someone else has written, and you look at it, you're like, yeah, this is so hard to read. It's probably easier if I just write my own parser framework, which I think very often is not really true. But we think it's true because we have practiced writing so much. That's where our fluency is. But we've never really practiced reading. We don't really have theories for reading. So of course it is hard. If I ask non-trained people to do a marathon tomorrow, they'd be like, that is super hard because I never did a marathon. But a marathon isn't inherently hard, right? I know if you've never ran a marathon, this probably sounds like terrible to you, but it isn't inherently hard. I mean, you can already walk. It's just you do that many, many times. It's only hard if you've never practiced. If you practice a lot, doing a marathon is not so bad, actually. And it's sort of the same with code, with reading code, where it sounds terrible, but that's because you never practice. But you could practice. You can actually get a lot better at code reading if you would just practice. So here's a few things that you can do. What I hope that you do after watching this video, the next time that you actually encounter code that is hard to read, I hope that you will reflect and you will think, okay, so that was uncomfortable. Is this a long-term memory issue? Is it just really hard because I don't know syntax? Is this a short-term memory issue? Is this just really hard because I have to remember many things and I don't yet know what is and what isn't important? Or is this a working memory issue where you're like, okay, I think I can oversee all the syntax elements and all the elements that play a role, but I don't know how they interact with each other. These three different problems have different solutions. So if your problem is, I don't know the syntax, then you can learn. You could practice syntax. I know it's not really a thing we do, but it works just really, really well. So you can make a stack of cards called flashcards, where on one hand side you put the prompt. So you, for example, in the APL example, you could put on one side the T, which actually isn't a T, it's called encode. And then on the other side of the card, you say encode. And this is how you could learn all the APL keywords that are all operators. But of course, this doesn't have to be APL. It can also be Python, where you say for loop on one hand side, and then the syntax of the for loop on the other side. Or if there's a certain API that you want to learn, retrieve a file, and then what you have to do is on the other side of the card. If you practice that, you'll get a bigger vocabulary of syntax. So then you're less likely to have these long-term memory issues. If you have working memory issues, on the other hand, if it's very, very hard to process the individual elements of code and how they interact with each other, you can support your working memory. Your working memory is basically, it's your short-term memory applied to a certain problem. So it also has this very small size limitation, but you could help it. For example, something you could do is you could have a tracing table like you see here, where you step by step analyze what's going on. So you say, okay, in the initialization, N is 7 and 2 is 7, very systematically. B string is the empty string and N1 is also 7. And then step by step, okay, loop iteration 1, this is what happens. Iteration 2, this is what happens. And you can do this manually, as you see me do here, but clearly, of course, this can also be done supported by an IDE, where you really systematically step through the code to try to gain an understanding and make it easier for your working memory to understand, because you offload the important information somewhere. And this could be on a literal piece of paper, or you can put all of this as watches on variables in your IDE, but at least you're offloading some of your working memory elsewhere so that you can process code more easily. So that is the good news. You can get better at reading code. Firstly, by self-reflecting and understanding what type of confusion are we dealing with. What you can also do as a really, really nice technique to remember code is, to diagnose code reading skills, is to remember code. So if I show this code to you for a little bit, just, well, maybe not half a second as I did with the sentences, but 3 minutes, for example, and then I take the code away. And now I would ask you, reproduce that code as best as you can. If you do that, you'll get a really nice insight into what you know. Because some of these parts, like the highlighted parts here, come from your long-term memory. Probably public class, public static void main. You didn't really remember that. You just remembered define a class and define a main method. And then later on, you use your long-term memory to reproduce the exact syntax, because you already know it. Whereas some things in this program, highlighted here in green, come from your short-term memory. Remembering that this was insert and sort, remembering that this variable was called array and the values in it were 45 and 12, etc. That is all coming from your short-term memory, and then it comes together. And actually at this time, little marketing from my research, we are exploring this. So if you're just interested in helping science figure it out, you can go to felienne.com/test, where we have a little memory exercise in Java for you. You don't have to do this right now, by the way, because the URL will also be at the end of the presentation. So you don't have to leave the stream and go straight there. You can do this later on as well. What you can also do as a great aid in getting better at reading code is to force yourself to summarize code. For example, look at code for 10 minutes. Just a number. It depends a bit on the size as well, of course. And then force yourself to write down, what was the goal of this course? Of this code? What are the most important lines here? What were the decisions that were made? What were the relevant concepts here? What are the things that really play a role? Both the domain concepts and also the programming concepts. And you might recognize this as an exercise if you have kids in high school, or if you well remember your high school days. You might recognize this as an exercise that is commonly given in natural language class, in English class. Kids would read newspaper articles all the time in high school and would be asked the exact same thing. Hey, here's a newspaper article, summarize this in 3 lines. This is like always on the SATs in the Netherlands, there is a question where you have to summarize text in a few lines. Because we know those are strategies that help you read natural language. Being able to quickly summarize something. Being able to quickly find what are the 5 most important lines of code here. And that's not something you just magically pick up. Those are skills you can also train. So if you want to get better at coding, in addition to understanding like why is this confusing, deliberately practicing reading code, for example by summarizing, is a really good technique. So if you want to know more about this, I just gave you like the taster of how knowing your brain's architecture can help you to become a better code reader and thus a better programmer. Definitely you want to check out my book, The Programmer's Brain on Manning. And you're in luck because tomorrow the book will be the deal of the day. So definitely be sure to follow me on Twitter. I'm @Felienne. Of course, follow Manning on Twitter as well, so you can get a discount if you buy the book tomorrow. And I think there's also some chat messages here by Manning that will also link to where you can buy the book. What you can also do as an alternative or an addition is start a code reading club. So many professionals that I've worked with over the last year and a bit have started to gain an interest in getting better at code reading. And there are ways that you can practice this as a group. And we started to call that a code reading club, where weekly or monthly, you just get together with a few colleagues. You take a piece of code from GitHub or from your own repo, doesn't really matter. And you just practice to systematically read a piece of code. It is a bit like a book club, where you all read the same book and then you chat about it. It is really like a book club, but then it's about code and you pick the code together. We found that is really a really great way to practice this skill of coding, of code reading, but also just a nice way to hang out with colleagues because, it's COVID time, so there's not a lot of social stuff going on. But this is also a nice way to interact with colleagues that isn't really about work. It is sort of enjoyable, but also it's very useful. We have a link also at the end of the talk. So that's it. That's everything I wanted to share with you today. Of course, there's still room for questions. So if you want to ask me anything, please put your questions in the chat. Before we go to answering the questions in the chat, let me summarize my entire talk in like 2 minutes, because I know I talk a bit quickly. I try to make it better, but it's just how I talk. I'm sorry. So to compensate, I have a little summary for you. So in summary, I have talked about how to read code. My name is Felienne. I'm @Felienne on Twitter if you want to follow me. Programming comes from a culture in which we very much think that by programming, you get better at programming, and that sort of programming is the only way to get better at programming. That culture is very visible also from the way we teach children. But research has shown that just by programming, you don't necessarily really understand what you're doing. Some kids might, but definitely not all kids will. If you want to be more systematic about getting better at programming, you have to know a little bit about how your brain processes things. And what you saw in the little experiment that we did with the 3 sentences is that what your long-term memory knows really helps how quickly you can process something. If you are looking at things you've never seen before, like APL or that weird alphabet that I invented, it's very hard to even process something. Whereas if you recognize some of the elements, it gets spectacularly easy. These different forms of memory create different forms of confusion. If you don't know a lot of syntax, you might want to practice syntax deliberately. If your working memory is overloaded by complex code, you might want to support your working memory by offloading some of your thinking to paper or to your IDE. There are many techniques from reading that you could use. For example, summarizing code is a very effective way to just deliberately practice reading. Like, as I said, in music, we practice notes. Like in tennis, you practice your backhand and your forehand. Practicing those small skills, this is not rocket science. Like, everyone does this. Math and language and sports and music. It's just time that programming also starts to do that. Remembering code is also a really great way to practice and also diagnose your own skill, because as you've also seen with the 3 examples, the more you remember, the more you already know. So as a way of diagnosing what you already know, remembering code can be really helpful. So that's the end. I will look at the chat after I finish these final slides. Again, my name is Felienne Hermans. I'm on Twitter at Felienne. If you want to check out my website's very easy. It's my first name, felienne.com. If you want to know more about the book that has chapters and chapters of more and deeper explanation about how your cognitive architecture works and how that matters for programming, whole chapters on picking the best variable names for comprehension, on refactoring your code so that it's easier to read, all of that, felienne.com/book, that will bring you to the Manning page where you can buy the ebook straight away and start reading straight away, or pre-order the print book that is coming out in spring 2021. If you're interested in listening to me and you really like listening to me so far, then you can listen to me a bit more for free. I'm also one of the hosts of Software Engineering Radio, one of the biggest software engineering podcasts on the web. We are on Spotify and iTunes in an interview format where me and other hosts interview famous software engineers, and every week a show comes out. If you want to help our research, if you go to felienne.com/test, you can participate in a little test. It only takes you like a few minutes to remember code and reproduce Java code, and it will really help support my research. So if that's what you want to contribute to, we'd be really happy if you would be interested in doing that. If you want to know more about starting a code club, we have free resources, felienne.com/club. It's all free. You don't have to buy anything. You can just get started with a starting package of exercises that we put on GitHub. So that's everything I wanted to share with you today. Let's just look at if there are questions in the chat. Awesome. People say, oh, Code Reading Club is such a good idea. I never thought about it. That's no problem. You can think about it now and start straight away. If you just find a few colleagues, like 2 or 3 colleagues, can already found a club together, and I promise you it will really, really be helpful and be a fun way also to interact with your colleagues. Cool. Well, thanks people also that are saying in the chat that they will check out the book. Of course, I'm really happy. You can start reading for free just to check out if you like the book before you buy it. And again, all my contact information is on the slide. So if you want to ask me questions, if you want to reach out to me, feel free to do so on Twitter or over email. My contact information on email is also on my website. Oh, good evening, everyone.
Oh. Cool. Thank you so much to Felienne for that great talk. I know she's not here virtually, but please give a little applause in the chat just so she knows that we appreciated her talk. As she's not able to field your questions live, we'd love it if you could send us your questions either via social media or via email or however you want to get them to us. I'm sure you'll find a way. You can post them in the LinkedIn event, that kind of thing. We are now going to give away a free JetBrains license and a free copy of Felienne's book. So we're first going to do the book, but to do that, if you haven't entered yet, go ahead and type hashtag CSC in the chat, and that will get you registered. Don't forget to follow us on Twitch while you're at it. Also, want to make sure that you follow us on your platforms of choice, be that YouTube, LinkedIn, you name it. And you can find all of those links at craftsmanship.dev. So our first drawing will be for a copy of Felienne's book. See how many times I can butcher it. I don't know why I keep screwing it up. All right. Ambrosia 86 has been drawn for the giveaway. Important thing, please contact Kat in the chat here. So Katzenbar, you want to post and if you don't contact Kat, we will draw another name. We need to make sure that we get this code to someone. Ambrosia, are you still? All right, very good. Ambrosia is here. We're going to do also to get a 35% discount on all Manning products. You can use this code MTPCSC21. That does not. We get no benefit from that. No, so don't think that we are doing this for the money or anything. It's just we are working with Manning to have some great presenters, and they wanted to give us this discount code for our members. Next, we're going to do the drawing for the JetBrains license. So while you're doing that, excellent. Thank you, Kat. Make sure that you're contacting Kat. While you're doing that, I do want to say thank you to all of our attendees. We love you. If you want to speak, we're currently finalizing our talk for next month, but we are also planning for the future. So there's a lot in the works. It's very exciting, and I think you're going to be happy about what we've got coming up. If you want to speak at Software Craftsmanship, or you know someone that we should reach out to, please let us know. And as always, we'd love to hear feedback. Is Software Craftsmanship really good? Are you enjoying this? Is there something that we could be doing better for you? And is there something, maybe a topic that you'd like to see in the future? You can email me directly at michael@craftsmanship.dev or find us in other ways online. I'm sure you can manage it.